Let's take a look at the sum and difference identities for sine, cosine, and tangent. What these identities help us do is understand how an expression like cosine of u minus v relates to cosine and sine of the component angles, meaning cosine of u, cosine of v, sine of u, and sine of v. It turns out that cosine of u minus v equals cosine of u times cosine of v plus sine of u times sine of v. This is an identity because it's true for any angle u and v. The explanation of why this is true isn't included in this video, but once we have this identity to start working with, we can use other identities that we know to extend this to a bunch of other expressions. So this would be a difference identity for cosine for u and v, the sum identity for cosine, cosine of u plus v, can be expressed similarly in terms of cosine of u, sine of v, and so on, by thinking of adding v as the same as subtracting negative v. And so what happens then, looking at the line above, I can simply replace all the v's with minus v's. And we get cosine of u times cosine of negative v plus sine of u times sine of negative v. But because of the even and odd identities, we know that cosine of negative v is simply equal to cosine of v, because cosine is even. And sine of negative v is equal to negative sine of v, because sine is odd. And so the sum identity for cosine becomes cosine of u times cosine of v minus sine of u times sine of v. To extend to angle identities for sine, we're going to use the cofunction relationship. So sine and cosine are cofunctions, which means that sine of an angle, let's say sine of x, is equal to cosine of 90 degrees minus x. So let's see how that helps us figure out, for example, sine of u plus v. I can turn that into cosine of 90 degrees minus u plus v, which, if I group that in a slightly different way, I can think of this as cosine of 90 degrees minus u minus v. And then from the difference relationship for cosine, going back to the difference relationship for cosine, I can think of that expression, but rather than u, I'm going to use 90 degrees minus u, and v, of course, is in the same situation as v up above. So I get cosine of 90 degrees minus u times cosine of v, and then plus, because of the plus sign up here, plus sine of 90 degrees minus u times sine of v. But then thinking about the cofunction relationship a second time, I can turn this cosine into sine of u. And I can turn sine of 90 degrees minus u into cosine of u. So we get sine of u times cosine of v plus cosine of u times sine of v. So once we have that, we can then figure out a difference identity for sine. To find a difference identity for sine, we can use the fact that sine of u minus v can be written as sine of u plus negative v. And so I get sine of u times cosine of negative v plus cosine of u times sine of negative v from the sum identity up above. And then using the even and odd identities, once more I get sine of u times cosine of v, because cosine is even, minus cosine of u times sine of v. So we just created the sum and difference identities for sine and cosine. We have the difference identity for cosine, we have a sum identity for cosine, we have a sum identity for sine, and we have a difference identity for sine. Let's use the identities we just developed to complete the following example. I'd like to find the exact value of sine of 15 degrees. Thinking about what we know about exact trigonometric function values, I know exact values for things like 30 degrees and 45 degrees and 60 degrees. And so I could convert within the sine function, I could think of the 15 degrees as being 45 degrees minus 30 degrees, because that difference is 15. And so the identity that I want to use is going to be the difference identity for sine. And we just found that sine of u minus v equals sine of u times cosine of v minus cosine of u times sine of v. So that means that this expression, sine of 45 degrees minus 30 degrees, is equal to sine of 45 degrees times cosine of 30 degrees minus cosine of 45 degrees times sine of 30 degrees. And for each of those we can find an exact expression. So thinking about the unit circle or special right triangles, I know that sine of 45 degrees equals the square root of 2 over 2, as does cosine of 45 degrees. And I know that cosine of 30 degrees is equal to the square root of 3 over 2, and sine of 30 degrees equals 1/2. And so filling in those values, I get the square root of 2 over 2 times the square root of 3 over 2 minus the square root of 2 over 2 times 1/2. So that gives me the square root of 6 over 4 minus the square root of 2 over 4. Or written as a single fraction, I get the square root of 6 minus the square root of 2 divided by 4. With a problem like this, we can check our work using a calculator. So I want to see that sine of 15 degrees equals that same amount. And so the calculator will give us a decimal value. We need to make sure that we're in degree mode. And then sine of 15 degrees, we see it's 0.258. And if I enter in using parentheses, if I enter in the square root of 6 minus the square root of 2, using parentheses around the numerator, and then divide by 4, we get that same value. So I can confirm that this makes sense, and the trig identity gave us a nice exact expression. So let me end with not so much a question, but a request for you to kind of check the following relationships. We have sum and difference identities for sine and cosine. For tangent, we'd like to come up with similar identities for tangent of u plus v and tangent of u minus v. Because tangent equals sine over cosine, we can use the relationships that we just created to show the following to be true. Tangent of u plus v is equal to tangent of u plus tangent of v divided by 1 minus tangent of u times tangent of v. And the difference identity for tangent is tangent of u minus tangent of v divided by 1 plus tangent of u times tangent of v. I hope you enjoyed the video. Thanks for watching.